Broadcasting from Studio 202 at the Springett Technology Center in Navasota, Texas, it's NOV Live. Now, let's start the show.
Hello and welcome to NOV Live. My name is Shelby Dumaine and I'm your host this morning. If you are watching this right now, that means you are watching us live. We are here, just like the intro said, we're here in Navasota, Texas in Studio 202. We have some really excellent guests that are here live in our studio, and we're going to introduce them in just a minute. But before we do, I want to mention we're talking about CCUS, What About Us, and a focus on small emitters. And before we introduce our guests and give you more on that topic, I wanted to go over to Kamalpreet Kaur. She's here to tell you a little bit about how you as an audience can get involved in the show live while we're talking to you. Kamal?
Thank you, Shelby. This is a live show, so if you have any questions for Brent or Spencer, who we have on the show tonight, please go ahead and put them down in the comment section, and we will address them at the end of the show.
Excellent. Thank you very much, Kamal. We look forward to seeing those questions. And once again, if you have a question, the best way to get them to Kamalpreet is by putting those in the comment section wherever you're viewing. All right. Well, without further ado, I want to go ahead and introduce our guest here in the studio. We have Spencer Oulman and Brent Staley. Can you, just to start off, can you all explain a little bit about who you are, what you do here at NOV? We'll start off with you, Brent.
Excellent. Thank you, Shelby, and thank you for having us on the show today. So my name is Brent Staley. I'm the Business Development Manager for our Low Carbon Solutions Group. And my focus has been on building our low carbon business here in North America, focusing on carbon capture, hydrogen production, and emissions reduction.
Excellent. Spencer?
Yeah, Spencer Oulman, Director of Innovation for PFT, Process Flow Technologies, with primary focus on low carbon solutions.
Excellent. We have two of our foremost experts, I'd say, here at NOV to talk about CCUS. So thank you for joining us. And with that, I know I've now said the acronym a couple times. Can you tell me and tell the audience a little bit about what is CCUS and what's the landscape of CCUS right now?
Absolutely. So CCUS stands for Carbon Capture, Utilization, and Storage. And it's a very hot topic in the industry, in the energy industry over the last year. And basically what it is it's a way for us to reduce our overall greenhouse gas emissions, specifically carbon dioxide. And in the global greenhouse gas emission, there are roughly 60% of our emissions come from power generation or industry. And basically when you consume or burn or there's a combustion of a fossil fuel, CO2 is emitted. And so carbon dioxide is an effective way to reduce those emissions by taking that carbon dioxide, and through there are various technologies that are used to take the carbon dioxide and capture it through a chemical process or other process, and then you take it and transport it and store it into a geological well permanently. Absolutely.
Yeah, I know I'm excited about CCUS because when I first started NOV, it felt like, it was this cool thing. And I was trying to tell my friends, if you're worried about, different energy sources, look at CCUS. And now I'm starting to hear on podcasts completely unrelated to energy or YouTubers, different people say, have you ever heard of this thing called carbon capture? And I'm like, it's getting out there. People are starting to understand it, like I said, outside of energy. So it's really exciting.
And a lot of folks look at it as a new technology. It's actually not a new technology. It's been around for 50 years. In fact, right now there are 35 facilities globally that capture carbon dioxide, and they store roughly 45 million tons.
Wow.
They capture 45 million tons of CO2 per year. Now there are goals and there are projects that are planned. There's roughly 200 projects in the pipeline. And by 2030, if those projects go forward, there'll be roughly 220 million tons a year of CO2 captured. Now, the Paris Climate Accord has some goals, and they see the IEA sees the carbon capture as an effective way to reach those goals. And their goal is by 2050, we should be capturing 4 to 8 gigatons of CO2 per year. So I think most folks in this space understand that we're behind.
Right.
But there is a lot of momentum, a lot of positive activity that is going on, a lot of government support, incentives that are being offered. The recent bipartisan infrastructure law and the Inflation Reduction Act have a lot of really great provisions to incentivize capturing your carbon. In fact, the 45Q tax credits within there were some enhancements that you can receive up to $85 a ton for the CO2 that you capture. So a lot of positivity, a lot of projects, a lot of hubs that are in development, that are going forward a lot globally, not just in the US, but globally. And so there's a lot of excitement in the industry. It's great to be part of it at this time.
Yeah, absolutely.
Yeah, it's also really nice too, because the carbon capture has been going on for quite some time. It's been predominantly looked at for EOR, for enhanced oil recovery. What's really nice with the bills that have gone through, and it's not just in the US, it's also across the world with some of the tax incentives or taxes that go on for CO2, is we're starting to see a lot of collection of ideas of how to do it better, because it takes a lot of components to make it work. It's not just about the capture, it's also about the transport, the pipelines, the storage, the landowners, it's the reverse of getting oil and gas out of the ground. It's like, how do you deal with a longer term aspect of putting it in the ground and keeping it there as well? So there's a lot of moving parts. There's a lot of entities associated with it, and that's really going to take a full momentum. It's not just a capture technology. It's not just a pipeline. It's all the pieces have to come together. So we're starting to see a lot of momentum moving towards getting things done, rather than just talking about it. So.
Right. It's always the exciting part.
Exactly.
I'd say. And I have some more questions, but before we get to my questions, I know y'all actually brought one in for our audience. So I want to go back to Kamalpreet, and she's going to tell us a little bit about a trivia question that y'all came here with.
Of course. And like Shelby mentioned in the beginning, that we are focused on the small emitters. So I would like to ask you, and put your answer down in the comment section, on what % of the US emitters will qualify as a small emitter. So that means they'll be capturing less than 500,000 tons of carbon per year. So go ahead and answer that in the comment section.
Excellent. Thank you, Kamal. So yeah, a little practice for if you have a question later. You can get used to where to put those by answering the trivia. So look forward to seeing people can get it. And I think we're actually going to reveal the answer here in a minute. So stay tuned. You won't have to wait too long. But before that, I want to ask y'all another question. I'll follow up. What are some challenges kind of facing the CCUS industry? I'm thinking well permits, what is energy penalties? Can you talk a little bit about those challenges?
Sure. So the first challenge I think that comes to everyone's mind is the cost to capture CO2 as it stands as a waste stream, right? So there's not a ton of revenue coming in for taking the CO2 and moving it, and we all so there are incentives and the cost of capture. And I think there's a graph that's up there.
Yep.
And so you look at some of the industries that we're talking about capturing CO2, and the ones near the bottom of the graph have a high purity stream CO2, high partial pressure, and so the cost to capture on those industries is relatively low, anywhere from $25 to $35 per ton. Now, if you've got $85 a ton coming in from the 45Q tax credit, that makes that economic challenge a little bit more feasible, right? But for the ones near the top, steel, cement, those are a little bit more challenging, because those dollars per ton they range anywhere from 60 to up to $100 to $120 per ton, depending on the technology, depending on the application and industry. And so the cost is something that's really challenging for carbon capture. And then you've got the cost to transport and also cost of storage on top of that. Another challenge, you mentioned permitting. In the US to permit a well to store CO2, it's called a Class 6 permit. And that's run predominantly through the EPA. Now, since the inception of this program of Class 6 permitting, there's been 2 wells that have been permitted. So there are quite a few delays that are that the industry is waiting for, and there's a lot of work happening, and I think they're going to get it. The other thing that's going on is states can apply for what is called primacy. So any given state can apply to the EPA to be able to take on that permitting themselves. And so there are only 2 states in the United States, North Dakota and Wyoming, that have primacy. Louisiana has just opened up to public commentary for their permit application, and everybody's expecting them to get that soon. And that will be a big kind of solution for reducing this bottleneck of permitting. But there are quite a few challenges for carbon capture currently.
Absolutely.
Yeah, and that comes back to that same value stream of, you can't just do it with one aspect. You have to have the place to put it. You have to have the ability to capture it. Economics have to work out across the line there. There's going to be economics that tie in. So somebody's going to have to foot the bill for it. Is it going to be over time? Is it going to be somebody that's actually developing it, and they're getting the funders in there as well? There's a lot of pieces that have to, moving pieces that have to come together. And if the cost structure isn't there, if the economics don't work, not saying it'll never happen, but things have to make sense. And I truly mean that in the form of dollars and cents, as if the economics don't work, it's going to be really difficult. But we're seeing, just like when organic fruits and foods came out, people paying more for services and food, there are some folks that are interested in doing the right thing. But from a global perspective on a larger movement, it's going to have to really make sense.
Right.
And it's been proven that storing CO2 permanently geologically is safe, but there's also the aspect of who's liable for that safety of that CO2 if something were to happen down the road. So, and then who's responsible for measuring and recording and verifying the exchange of those CO2 along each section of the value chain. A lot of solutions being developed and put forward in the market in this instance. And so it's the challenges are there, but I'm super confident that this is something that we're going to figure out just in time. And it's exciting that it's going forward in the way that it is, and there is so much momentum.
Yep. And with that, I would like to reveal our trivia question. I think that kind of plays nicely into what we're talking about and what we're going to talk about next. So we'll go to Kamal to reveal it, but then I'd like for y'all to talk a little bit more about it. So Kamal, can you reveal that trivia question answer?
Of course. So the answer is, for the question, what % of the U.S. emitters will qualify as a small emitter? So that means less than 500,000 tons of carbon emitted per year. And the answer is 81.4%. So that will equate to around 3,800 facilities in the U.S.
We should probably say before we get any people countering that was 2020 EPA data. So yes, it is changing. There are different facilities. So just in case there are people contesting that
Anyone
answer.
fact checking. Fair. Can you talk a little bit about what that means to the small emitters, small facilities? Can you explain that a little bit?
Yeah. So capturing CO2, when economies of scale are at play and you're capturing millions and millions of CO2 per year, that makes the financial equation more desirable, right? Because you're getting more dollars per ton. But for the smaller facilities, smaller emitting facilities, 200, 300,000 tons per year, the economies of scale are not at play. And so that cost per ton of CO2 is higher, and it makes it so it's not a feasible option for the smaller facilities. And there aren't a whole ton of solutions that are out there, but it's something that NOV that we're focused on is when you're talking about capturing CO2 from any given industry, from steel, from cement, from power, you're not talking about capturing CO2 from an industry. You're talking about capturing CO2 from a specific point source.
Right.
So we're talking about boilers, we're talking about heaters, cogen units, natural gas compressors. And so each of those point sources have a CO2 composition percentage profile and a given range of CO2 volumes that they emit per year. And so what we're doing is we're developing, and Spencer's been doing some great job, and so I'll let him continue the point. But what we're doing is developing solutions for specific point sources that can be standardized to be able to bring those economies, that financial economic equation more in the black for smaller facilities.
And we had talked about kind of the action instead of just speaking on it. So that was what I was going to ask you actually, was how are we addressing these challenges maybe from a technical standpoint?
Sure. I was going to say that image that was just behind Brent a second ago, that is not that one, the one before.
Oh, the graph.
No.
Do you want to pull it up? Oh,
there
this one.
that one.
I love this one, the photography.
Yeah, so this is a rendering of what a facility looked like for about a 400,000 ton per year capture plant.
Wow. I'll be honest, it fooled me. I just said it's great photography. It's a render.
Great image. Not
great image.
But it kind of gives some perspective on the technology that needs to go into it. And what you're really looking at is a couple of very large towers. The tallest tower on there is really the absorber, which is taking the flue gas in. So the bulk gas, whether it's 6%, 4%, 12% CO2, it's the most gas, and most of it is going to be nitrogen. It's going to be the whatever the combustion products were, but most of it's going to be typical air that's coming in and then combusting the products coming out of it. So really, it's just a very large volume, and that's where the solvent technology is in contact with the flue gas. That solvent then goes over, and then the desorber is the smaller, skinnier column to the left of that. And the output from that is basically the gas coming off the desorber is the CO2 that was in the flue gas. So you're kind of taking an absorber section, which is in contact with the gas stream. You're then taking the solvent and basically releasing the CO2 from that. And that's the premise of the solvent carbon capture system. But then you're going to have cooling systems on the backside, so direct contact coolers, that back one on there, and then there's a solvent storage tank on the front side there. So really, it's a bunch of equipment, but there's not a lot of moving parts. There's not a lot of, other than gases and fluids interacting with each other, there's not a lot going on behind the steel columns there as well as stainless steel. Then there's heat management, there's liquid management, there's solvents, there's reclamation. There's a lot of other complexity goes onto it, but the simplistic view of it is there's an absorber, a desorber, and the system supporting those two systems overall. So that's kind of at the higher end scale of where we're at. Most of the projects that have gone forward have been that, if not 5 times larger than that.
Right.
So like the Nova facility that's being looked at starting back up in Houston, that was in the multi-million ton per year capture range. So much larger absorbers, heavy on the engineering side, a lot of time that goes into that aspect as well. I think we've got a section we'll talk about some of the things that are going to be looked at here for standardization as well. But the technical pieces are, how do you make it smaller? And you run into some challenges on what's taking place in those columns when you make it smaller. There's going to be wall effects. There's going to be pressure drops that have to be kind of balanced out on there. It becomes challenging. That scale doesn't work on the downward side. It really does work more favorably towards a lower cost of capture per ton at the larger scales. Most of our efforts are really trying to get into how we can standardize it, how we can get rid of the custom engineering aspects of it to reduce some of the time, but also reduce the costs. And the other image you guys had up first is kind of the other end of the spectrum.
Yep.
And we'll be previewing this and showcasing it later this month, kind of a unsolicited plug here, fully solicited for June 28th, June 29th at the CCUS conference in Houston at Energy Center.
I'm glad you said I was going to ask about it anyway. So.
Perfect. But we'll be showcasing that technology. We've got a little concept tester to kind of get the minds wrapped around what we're doing on there. But you'll notice that there's no tall column on here. And what we're really trying to do is you get rid of the vertical tower. Now you have the ability to start doing things of more manufactured scale, more modular aspects, and the ability to use parametrics to, okay, how much gas do you have? This is what your size of your absorber unit's going to be. More tubes, more like a membrane system where you're using standardized tubes, and the number of tubes really equates back to the gas volumes going through there. And on the desorber side, it's how much solvent relative back to the CO2 concentration goes in there as well. So same concept, just taking vertical and making it horizontal so we can actually ship things around. We can move things, we can deploy them much faster, and hopefully take advantage of some of the manufacturing practices and leaning out the cost as well. And that's really the key, is making it cost effective, because we are talking about handling a waste stream at the end of the day.
Right. And this is when we're talking about a lot of this. Am I correct? This is a lot with the process and flow technologies business unit. Is that?
That is correct.
Yeah. I mean, talk about the experts in this. I mean, that's a great, I feel like y'all are perfectly positioned for this kind of developments as well.
Yeah. PFT and well stream processing and the legacy behind that have been handling gas and liquids and solids and liquid separators and deoilers and desulfonators, hydro inhibition technology for decades. And we're basically just applying the same principles into a fashion that fits within the CCUS space.
Right. We talk about that a lot. Oh, sorry. Go ahead.
I was going to say the large projects, the multi-million tons per year, those are always going to need a bespoke solution, a customized solution for those. But so where our efforts and our focus is in for the smaller facilities is you can standardize that system, and all all carbon capture projects today are starting from a blank page. And there's a lot of inherent engineering costs and other costs and delays in starting from a blank page. And so what we're trying to do is offer a solution to the market that is a more standardized approach to bring down those costs and reduce the time to deploy these to market.
Right.
And in this way, it really can make those smaller facilities a reality, make carbon capture a reality for them.
Absolutely. And like we mentioned, that's 81.4%. So there's a lot out there who could use it.
3,800 facilities just in the U.S. alone, and that's just the below 500,000 tons per year. That doesn't include the smaller emission points within larger facilities that are actually above 500,000 tons. But like we've been talking about working with refineries and other facilities, that you may have 2 miles between emission point sources. You're not going to route a 30 or 40 inch ductwork for 2 miles across a refinery. You'd be laughed out of the facility before the operations team even had a chance to listen to anything beyond that. So having the ability to look at decentralized absorption technology and centralized desorption technology, now you have the ability to kind of separate those two, where in that previous graphic that showed them right next to each other, you may need to have the facilities and not handling the large gas streams at different locations. So kind of getting in the weeds of the details and complexities, but there's a lot that's going to go into, and that's why I kind of mentioned the parametric. It's not really standard. Standard is there may be ways to take the Lego pieces and move them around in ways that make sense for the facilities. But back to the bespoke side is, when you're at that scale, the efficiencies on the energy usage, you really don't have the luxury of taking pure standards at very large scale. You want to take advantage of every last drop, every last BTU you can take out of a facility to handle power and energy and things like that as well.
Yeah.
And I would say we've kind of shown the spectrums, but there's a spectrum beyond that in complexity, which is more the traditional power plants. But we got two more levels beneath this, where the Summit solution that we got on here is more of the highly customized, but still taking advantage of some go-bys from a engineering standpoint. And the next level down is going to be on the peak side, which is using some standards, but still having the flexibility to bake it in and build it into existing facilities. And there's one below that, which is going to be on the ascent, which is what can be moved down the road, putting modules in place that are easily transported, dropped off, deployed. And then the approach was the last one, which is that horizontal, which is really you want 2 or 4 or 6. It's really a numbers game of how much gas you have. And then it's also a standard size for each of the components. But it's, again, still Lego blocks. And recognizing there's going to be layout constraints and considerations for sites as well. So.
Absolutely.
It's a good place to start too. There's been this approach in the industry of capture all your CO2 or capture none of your CO2, which I think is debilitating to our progress in the decarbonization effort. And this way you can capture, you can focus on 1 or 2 of your point sources in your facility, and then you can push the cash flow to the right and fund your future capture projects with the current funding that you're getting in revenue that you're getting from your current carbon capture projects. I think that's a more reasonable approach to the decarbonization efforts. We've got to start somewhere. As we talked about earlier, we're behind. And so you got to start somewhere and make some meaningful progress. And I think this is a great way to start that.
I wanted to ask a little bit more. We've talked about, like you said, the revenue, the different economics, the cost associated. Can you talk a little bit about what the economic implications are for developments when it comes to carbon capture and storage?
Sure. So there's a lot of, I mentioned the government incentives that are currently 45Q tax credits and $85 per ton. There's also the voluntary carbon offset market that is being established and kind of emerging. And currently the way that we're modeling that, I think most folks look at it in the low 20s or high teen dollars per ton for carbon offset market. But that's significant revenue if you're talking about hundreds of thousands, if not millions of tons of CO2 per year. And then, this is a great way for folks to meet their 2030, 2050 carbon footprint goals. And so I think the economic evaluation and the way that they're looking at this is, okay, what is the plant life for 20 to 25 years, and then project how much CO2 you're going to capture in the 20-year life, and then how much revenue you're going to get from the CO2 that you capture. And that's kind of how people are developing this economic model, looking at, a dollar per ton figure. Some folks are looking at it as, I want a turnkey solution. So I don't want to worry about those tax credits. I don't want to worry about any of the operations. You come in and you provide me a solution. And so consortiums are being developed that take care of the whole value chain of capture, transport, and storage. And it's really interesting. There's kind of unique commercial arrangements that are being structured, and it's really unique. And I think it's needed. All the creative solutions and approaches it'll be a cocktail of solutions that kind of go forward. But I think it's a reality. It's really becoming a reality.
It's exciting to hear.
Yeah, there's a lot of complexity in these systems and solutions and projects, and it's geographical and it's governmental. Some governments have different incentives. Some geographies and geologies are more suitable for some of the systems to go into place. For any of the pipeline or midstream folks that are on the call, they're probably wondering, how are you going to pipe a small scale facility? Well, that also comes back in the perspective of there's going to be clusters of these clusters and hubs, depending upon how and who you talk to. But more than likely is when you get a large power plant, there's going to be other facilities nearby. They're going to be taking advantage of that. Industrial complexes, Like the Gulf Coast around Houston and Louisiana is an ideal spot when it comes to all of the industry that's there, all the furnaces, all the boilers, all the refineries. Those are all point source that we take advantage of. And the prognosis over the next 30 years from pipeline standpoint is there will be a lot of emphasis around how to bring more pipelines in to handle that and get it out to the right places as well. But right now there's discussions on local geology for capture and storage. There's also offshore, there's deep sea, there's all sorts of different ways they're being looked at. And the logistics are really the crutch of it. Is technology's there. We know how to handle CO2. We've been doing it for many years for EOR. We've been using it. We've been doing it for offshore, coastal Brazil example, for handling high CO2 gas streams. So handling it, pumping it, compressing it, whether it's supercritical or it's liquefied or it's gas, all that technology exists. The crux really comes down to is how do you do it in a way that makes sense for the local regions, for the emission sources, and how do you get it to places that are most sustainably put in place for storage and for the future of beyond EOR. And that's probably another chat to come, much more than a 30-minute conversation just on that alone. So,
well, that's what I think this is a perfect example of. We've seen a lot throughout NOV when it comes to these kind of, I don't know if green's the right word, but these lower carbon or these kind of the future solutions we're looking at, which is it might be a complicated a challenge to face, but come to the experts who have, like you said, well stream and process and flow technologies. We have the legacy there, we have the knowledge, and we got the people here in the room, but in the company who can help answer that really challenging question.
And kind of touch on that is it's almost like if we can make it as simple as if people think that all gasoline is a pump and you just put it in your car, you're forgetting all about the upstream aspect of that goes all the way back into where it's coming from and how it's processed. And we're trying to make it that simple as well, so that the users and the developers are looking at it simplistically, where provide this to us, and you and I and everybody else that's paying per kilowatt hour on their homes, you don't really have to think about how to manage that as well. So
right. Well, I've been hogging y'all long enough from our audience, so I want to make sure I give them a chance to ask you their questions. So with that, Kamal, do we have any questions from the audience?
We do. So David Hernandez on LinkedIn is wondering what happens to carbon once it is captured.
Oh, okay.
Do you want to touch on that?
Sure. So once the CO2 is captured from the capture facility of the pictures that we showed, it then must be conditioned, because carbon dioxide off of a flue gas is atmospheric conditions. It's very wet. And so water and CO2 combined makes carbonic acid. And so you can't throw it into a pipeline without significant challenges and problems down the road. And so
carbon steel pipeline.
It's carbon steel pipeline, exactly. So it has to be dehydrated, conditioned. In some cases, depending on the pipe spec, you have to remove some oxygen as well. And then it has to be compressed. And depending on what you're doing with the CO2 at that point changes how you deal with the CO2 at that point. If you're going to put it into a pipeline for a sequestration well or EOR field, then you've got to you want to compress it to supercritical CO2. That's a dense phase CO2 that acts almost like a liquid, because the energy requirements to move it at that point are a lot lower. So it's a lot more economic to move it using booster pumps rather than compression. And so you bring it to supercritical CO2, and then you throw it into a pipeline to move it to a sequestration site to store into an injection well, and it's stored there permanently, or moved into an EOR field to use to enhance oil production. But inherently, the CO2 also quite a bit of it is stored in the rock, in the pores of the rock through enhanced oil recovery. There are the utilization aspect that Spencer talked about. There's a food and beverage industry that uses CO2 that you'd have to liquefy it at that point. So that becomes a different process other than supercritical CO2. And so there's quite a bit of refrigeration and liquefying in that process. And that's basically those other the utilization technologies that are being developed and advanced. There's a lot of great ones for aggregates into the concrete industry and cement industry. There's the syngas and synthetic methane for converting the CO2 into something usable, but the demand is not there to take the volumes of CO2 that we're talking about. And so the reality is the solutions going forward right now for taking that volume of CO2 is going to be storage, geological storage.
Right. And so that's kind of when you hear people say CCS as opposed to CCUS. We're talking about that carbon capture storage.
Yes.
And then the U is the utilization is where that comes in.
And some people use utilization, some people
Right.
use conversion. Utilization typically in most people's minds means EOR, and that's the vast majority of the utilization is used for EOR. It's not a bad thing. It's basically displacing oil underground, and it is keeping it in the ground just like a Class 6 well would be keeping it in the ground. But it's actually doing something productive on the backside. So there's different levels of 45Q. There's different levels of incentives when it comes to what it's going into, what it's being used for.
Wow.
But as Brent was saying, the vast majority of CO2 will likely be going towards storage or sequestration. And that's just sheer numbers of when you're talking 4 gigatons or 8 gigatons of CO2. I like the analogy Brent uses on presentations talking about the Dallas Cowboys football stadium, of how many stadiums it is. And I think it was like 38,000 Dallas Cowboys stadium per year, something like that.
So currently of the CO2 we're capturing, it's 7,700 Dallas Cowboy stadiums. To reach 4 gigatons, it's 787,000 Dallas Cowboy stadiums.
There.
Yeah.
And not sure exactly where the trajectory on the question was, but talked about conversion, talked about the transport, and I kind of interluded about the carbon steel pipeline because NOV also creates fiberglass and composite pipelines and flexibles. And I emphasize the carbon steel because if you switch over to fiberglass, there's opportunities to avoid some of the issues with the pipelines, and the moisture spec and things like that can change as well. But because
it's not a problem with fiberglass, it can handle 100% wet CO2.
Moisture is not an issue. Water slugging and just general hydraulics of the pipeline are another issue. But if you do the numbers on where we're trying to get to by 2050, there's only so much aggregate that you can actually take advantage of. There's only so much you can think about from a conversion of CO2 into methanol or other types of materials.
Right.
And that has to be kind of balanced out. There will be opportunities. However, the vast majority is more than likely going to be going to storage for the.
And we're fully supportive of those technologies being developed. In fact, NOV, we often look for opportunities to help and support technologies that are doing that, because that offers an additional revenue stream to help support carbon capture overall. But again, like Spencer mentioned, and I mentioned earlier, the volumes, the sheer volume of CO2 is just, it's hard. And that's why I created that football stadium, is because what is a gigaton? Like, how do you quantify that in your mind? And so something visual I thought was one of the largest, stadiums in the NFL. So
it's like the Moore's law of carbon capture. It's just using Dallas Cowboy stadiums.
Exactly.
Yeah, I love it. I love the visual. Well, come on. Any other questions from the audience?
We do. We have one more question. So this one comes from Naeem on LinkedIn, and he's asking, how do you see your capture facilities working with CO2 leakage, sensing products, and data aggregation for performance?
So I won't call out the company that Naeem works for because it's specifically back to his focus, but it's a great question in the sense of how do you assure that what you're doing on the capture plant is actually going towards something useful rather than just, again, further leaking the CO2 back out there or from the well or otherwise. And that's a whole nother area of the industry it's going to have to be looked at, because you do it, it's kind of like a LACT unit on a traditional oil field, is you want to basically have a transference of, and at the end of the day, when you're saying you're doing it, there has to be some sort of verification process to that. So I think the terms are very similar for oil and gas production. On this case, it's how do you make sure it's going into some place and it's actually staying there.
Right.
And that's part of it comes back down to the government as far as what the regulations are. Some of it's going to become industry standards. There will very likely be API standards that are put in place to support these activities. But the monitoring side, the measurement side, it's not an easy one. And Naeem and I have had conversations on this in the past. It's on the grand scheme of things, it's relatively easy to measure methane against background because there's not that much methane in the atmosphere. But when you're measuring CO2, small leaks against a background of 420, 440 ppm, there's a lot of background noise there. So there's going to have to be a lot of effort on the sensors and on the technologies to really measure that. And it's going to be somewhat on the sensor side. It's going to be somewhat on the process assurance within the control systems, within the pressures, and basically looking at the full thermodynamics process from start to end, all the way to the reservoir and the formation, and monitoring that over the years of the flow of the CO2 throughout the formation. So it's a very complex and appreciate the question, Naeem, and appreciate you putting it right square front and center of the difficulty of the nature as well. So
it is crucial because
Yeah.
you're going to spend millions of dollars in infrastructure to capture the CO2. There's got to be some verification that it's not just going to leak back out, but also monetizing CO2. There's got to be some verification that you're actually capturing the amount of CO2 that
Right.
you say that you're capturing.
Yeah.
And so that's a big part of the challenge as well.
That's right. Excellent point. Well, I have one more question before I let y'all go. How can folks learn more about CCUS or CCS? I know we talked about it a little bit. We teased it a little bit earlier in the conversation.
So of course, they can reach out to me or Spencer on LinkedIn.
Mhm.
I think there's an email address that we're going to pop up here in the end. You're welcome to reach out to us that way. But
Yes.
NOV.com/CCUS is a great way to see all the products and services that NOV, because we really have just, other than fiberglass, we just kind of scratched the surface for all of the things that NOV does in the carbon capture value chain. We have plastic internal coatings in our Tuboscope group.
I was gonna say we were actually having Tuboscope on, and I want to say 2 weeks. Don't quote me on that, but I think 2 weeks to talk about CCUS as it pertains to
Fantastic.
Mhm.
Pumps for moving CO2. He talked about our offshore footprint of our carbon capture and storage products is very well known. So there's lots of other things that happens at NOV. You can learn more about that at NOV.com/CCUS.
Rabbit hole goes down a long way.
Absolutely.
That's right. And then in
come
person,
visit
right?
us
That's right.
June 28th, 29th at NRG. Great convention. It's a lot of different technology providers. It's everything from measurement. Last year, there were folks on tax. There were conversations from, I think Brad Crabtree was there last year, if I remember right, or somebody from the DOE that was there talking about the government programs that are going on. But it was probably one of the better holistic sessions. It was not just about midstream. It wasn't just about the capture technologies. It really was the full value chain of what's being focused on here.
And we will have a booth in several, I think 6 or 7 of our business groups that have carbon capture and storage products will be at the booth. You can come and meet us, and we'd love to meet you and connect and see how we can collaborate and work together on making this happen.
Absolutely. And if you keep an eye on, I know NOV's socials, Twitter, LinkedIn, Facebook, you will be posting more about the booth number, where to find us, who will be there, so audience kind of stay tuned on that. And y'all did mention the email. I'm going to go to Kamal real quick. Kamal, can you tell us what that email is? They want to get in direct contact with the team.
Of course, please go ahead and contact us at pf-ccusmarketing@nov.com. So once again, pf-ccusmarketing@nov.com.
Thank you, Kamal. This is why we have Kamal here, because I knew I would not remember that off the top of my head. So
Maybe
we have that, and we have it on the screen.
Maybe we can put that in the show notes or on the screen.
Yeah, it'll be on the screen. Yep.
Absolutely.
Yep. Excellent. Well, I just wanted to say thank you so much for joining me today live in the studio and talking to our audience. So thank you, Spencer and Brent, and thank you, Kamalpreet, for joining us as well and asking those audience questions. And I can't help but give a shout out to our production team as well. We have Amanda May, Quinn Liu, and Aaron Williams. Thank you so much for all of your help on the show today. And last one, thank you for tuning in and for watching this. My name is Shelby Dumaine, and I've been your host today. Thank you for joining, and we'll talk to you next time.